Lesson 27, the binomial probability distribution. The binomial probability distribution calculates the probability of getting a certain amount, x, of one possible outcome out of a total number, n, of attempts, when each independent attempt can result in only one, with probability p, of two possible outcomes. Now, the binomial probability distribution, like all probability distributions, only calculate probabilities for the specific situation that they were intended to. Thus, the binomial probability distribution can only be used to calculate probabilities that match this situation. That is, when each independent attempt can result in only one of two possible outcomes. Hence the name binomial, bi meaning two and nomial meaning outcome. So when a random process can result in only one of two possible outcomes, and we want to answer probability questions regarding the number of ways that that result can occur, we can use the binomial probability distribution. For instance, when a coin is tossed, the result can only be one of two things, heads or tails, two possible outcomes. Hence, if we wanted to answer probability questions regarding how many times the coin will come up heads or tails, we can use the binomial probability distribution formula. Also, whenever a bet is placed, there's only two possible outcomes. You either win the bet or lose the bet. And so placing a bet results in two possible outcomes every time the bet is placed. If we wanted to calculate probabilities regarding how many times we either win or lose that bet, we can use the binomial probability distribution formula to answer those questions. Also, every time a child is born, the result can either be a boy or a girl, two possible outcomes. So if we want to calculate the probability of having so many boys or girls born, we can use the binomial probability distribution to answer those probability questions. So the binomial probability distribution formula can be used to answer numerous probability questions, as long as we focus on particular events, and looking at either that event occurs or that event does not occur. Looking at the problem in this way creates a binomial random process. Now, just because a random process can result in one of two possible outcomes doesn't automatically make it a binomial probability distribution. It's also important that each attempt be independent of one another. And independent means that the result of one attempt does not affect the result of the other attempts. So as long as the attempts are independent, the binomial probability distribution applies. But if one event does indeed affect the other attempt, then the binomial probability distribution will not apply. So now, in order to calculate probabilities using the binomial probability distribution, the values of the three variables, n, p, and x, must be determined. So when you learn and study the binomial probability distribution, you must be able to focus on the values of these three variables, n, p, and x. First, n. N represents the total number of times the binomial random process is being repeated. So even though in the binomial random process it can result in only one of two possible outcomes, overall, this random process is repeated several times. That is, when you toss a coin, the coin is tossed more than once. Or when you place a bet, you make that bet more than one time. Or when a child is born in a family, we could have more than one child. So n represents the total number of attempts. P. P represents the probability that one particular outcome occurs each time the binomial random process is conducted. So each time the binomial random process is conducted, there's a specific event that we're interested in, and it either will occur or not occur. P is representing the probability that it will occur every time that random process is conducted. And that probability P needs to be the same every time this random process is attempted. X represents the value of the binomial random variable for which the probability is being calculated. So there's a particular probability question that we're trying to answer. X represents the value of that random variable that matches the particular probability question that we're trying to answer. Now X is a count, or a frequency. So it's basically counting the number of ways that that particular outcome occurs out of the total number of outcomes. As such, the binomial random variable X is discrete. That is, it takes on whole numbers only because it's a count. And the possible values of X are X equals 0 at the lowest, because we always start our count at 0. And then we count our way through the whole numbers, 1, 2, and so on, all the way up through n. N, the total number of attempts, is the highest the random variable can be, because we can never get more than the total that we have. So the total possible values of the binomial random variable X always range from a low of 0 to a high of n, the total number of attempts. The binomial probability distribution formula is given by the following equation. Fortunately for us, this formula is programmed into the TI-84 calculator. The binom PDF n, p, x command on the TI-84 calculator calculates the probability of p sub x. Binom, short for binomial, PDF, short for probability distribution formula, is the command name the TI-84 calculator uses to program the binomial probability distribution formula. And the way it works is you have to enter the three values, the n and p and x, into the calculator in this specific order. N always goes first, p goes second, and x goes third, separated with commas. And the calculator will take those values of n, p, and x that are entered into the binomial probability distribution formula and use them to calculate the probability of equaling the entered x value only. The binom CDF n, p, x command on the TI-84 calculator calculates the probability that the random variable x takes on values that are less than or equal to the particular value of x that's entered into the calculator. That is, the values of the n, p, and x equals 0, 1, 2, all the way up through the specific x value that's entered into the command are entered into the binomial probability distribution formula, and the resulting probabilities are summed or cumulated. Hence, the abbreviation CDF is representing cumulative. That is, it keeps a running total of all the probabilities, always starting at the 0, the lowest value of x, and accumulating or adding the probabilities all the way up to the specific x value that is entered into the binom CDF command. For instance, if a fair coin is tossed 10 times, the probability that exactly 5 of those 10 tosses result in heads is given by the binom PDF 10, 1/2, 5 command on the TI-84 calculator, where here the question is asking for a probability. The binom, short for binomial, is used here because this problem follows a binomial random process, since tossing a coin can result in only one of two possible outcomes, heads or tails. The probability question is the probability that exactly 5 of those tosses results in head. And because we're only interested in the value of the random variable x equaling 5 exactly, we use the PDF command, because the PDF calculates the probability of that one particular x value result. The first value entered into the binom PDF command is n, the total number of attempts. In this instance, the coin is tossed 10 times. So when the coin is tossed a total of 10 times, n equals 10. Comma, to separate from the second number, which is the p. In this case, a fair coin is tossed, and the focus is on the result being a head. So p would represent the probability that a head occurs anytime a coin is tossed. And because it's a fair coin, the probability it comes up heads is 1/2, 1 out of 2. So now we can enter this command into the TI-84 calculator to get the probability result. The probability distribution functions that are programmed into the TI-84 calculator are found in the distribution menu. This is the second function that the vars button does. So when you press second, vars, it gets to the DISTR, short for distribution menu. And then using the down arrow, place the cursor next to the probability distribution function you want to calculate. In this case, we want to do the binom PDF. So with the cursor next to binom PDF, we press enter to select. And then the first number we enter into the command is in the total sample size, in this case which is 10, comma, to separate it from the second value, which is the p. The probability in this case is 1/2. We could enter it in as 1 divided by 2, comma, and the last number we enter is the value of the random variable x that we're trying to find the probability for, in this case 5. Close parenthesis, enter. And here we have the probability. So the probability rounds off to about 0.246. Hence, if a fair coin is tossed 10 times, the probability that exactly 5 of those 10 tosses results in heads is 0.246, or 24.6%. For instance, if a fair coin is tossed 10 times, the probability that 5 or fewer of those 10 tosses results in heads can be calculated by using the binom CDF command 10, 1/2, 5 on the T84 calculator. Here, the binom command is used because this follows a binomial random process, since tossing a coin can result in only one of two possible outcomes, heads or tails. And because the question is what's the probability that 5 or fewer of those, that is, the value of the random variable x needs to be less than or equal to 5, we use the binom CDF command. CDF cumulative, meaning we're going to add up all the probabilities starting at the lowest value of x, which is always 0, and going all the way up to the particular value that's entered into the x for the binom CDF command, in this case 5. So this result will find the probability of all the values less than or equal to 5, that is from 0 to 5. In, the first number in the command, is the total number of attempts. In this case, the coin is tossed 10 times, thus n equals 10. The second number is the p. In this case, a fair coin is tossed, and we're focusing on the result being a head. So p would represent the probability that the coin comes up ahead every time the coin is tossed. In this case, it's 1/2. So now this command can be entered into the TI-84 calculator. The binom CDF command is found in the distribution menu. We get to that by pressing second, DISTR. Then we arrow down till we find the binom CDF command. And with the cursor next to the binom CDF command, we press enter to select. And the first number we enter is in, which is 10, comma, the second number is p, 1/2, or 1 divided by 2, comma, and the third number is the x, which is 5. Close parenthesis, enter, and here's our probability answer. So the probability rounds off to about 0.623. Thus, if a fair coin is tossed 10 times, the probability that 5 or fewer of those 10 tosses results in heads is 0.623, or 62.3%. The mean for the binomial random variable x is given by the formula mu sub x equals n times p. And the standard deviation for the binomial random variable x is given by the formula sigma sub x equals the square root of the quantity n times p times 1 minus p. Now, of course, we could use the 1var stats command on the TI-84 calculator to calculate the mean and standard deviation for any random variable. But if we happen to know that the specific problem we're dealing with is a binomial, we can use these formulas to calculate the mean and standard deviation. To calculate the mean just requires one multiplication of n times p. And to calculate the standard deviation just requires two multiplications, a subtraction, and a square root. This is a lot less keystrokes to do than using the 1var stats command on the TI-84 calculator, because to calculate the mean and standard deviation for a probability distribution, you have to enter the entire probability distribution into the list. For instance, list 1 would have to contain all of the values of the random variable x, and list 2 would have to contain all the values of the corresponding probabilities. And then using the one-var stats command, list1 comma list2 would calculate the mean and standard deviation. But if we happen to have a binomial, just multiplying n times p to get the mean and square rooting the quantity n times p times 1 minus p to get the standard deviation would be a lot more efficient. For instance, calculate the mean and the standard deviation for the random variable x, which represents the number of heads observed when a fair coin is tossed 10 times. So here we're going to calculate the mean and the standard deviation. That is, the mean mu sub x and the standard deviation sigma sub x. Now here we notice that this random variable x represents the number of heads observed when a fair coin is tossed 10 times. This follows a binomial random process since tossing a coin can result in only one of two possible outcomes. That is, it's either a heads or a tails. Therefore, we can use the binomial formulas for calculating the mean and the standard deviation. Here, for the binomial, mu sub x, the mean, is equal to n times p. And the standard deviation sigma sub x is equal to the square root of the quantity n times p times 1 minus p. Thus, we just need to determine the particular values for n and p in this problem to calculate the mean and standard deviation. N represents the total number of attempts. In this case, the coin is tossed 10 times. Hence, n equals 10. And since the coin is fair, p represents the probability it comes up ahead anytime the coin is tossed. P would equal 1/2. So using the value of n equals 10 and p equals 1/2 in these formulas, we find that the mean, mu sub x, is equal to 10 times 1/2, and the standard deviation is equal to the square root of the quantity 10 times 1/2 times the 1 minus 1/2. So we could calculate these results on our own if we want, but we could also use the aid of the calculator to do some of the work here too. To calculate the mean and standard deviation using the binomial probability formulas, I'll press clear to clear the screen. The mean mu is equal to n times p. N was 10 times p was 1/2. 1 divided by 2. Enter. So the mean is 5. Sigma, the standard deviation, is found by taking the square root. The square root is found by going second, and the x squared button gets you to the square root of n, which is 10, times p 1/2, 1 divided by 2, times left parenthesis 1 subtract p, which is 1/2, 1 divided by 2. Right parenthesis to close that one, and another right parenthesis to close the square root function. Press enter, and the standard deviation is about 1.6. Thus the mean, mu sub x, equals 5, and the standard deviation sigma sub x rounds off to about 1.6. Thus there's our result. The mean is 5, and the standard deviation is 1.6. This is telling us that when a coin is tossed 10 times, we expect about half of them, or 5, to come up heads. But because this is a random process, we don't always get 5 heads out of 10 tosses. Sometimes by chance alone, we get a few more heads or a few fewer heads when we toss the coin 10 times. The standard deviation is telling us that on average, this is how much the particular number of heads deviates from this mean of 5. So on average, the number of heads can deviate from the mean of 5 by about plus or minus 1.6 heads on the average. The binomial probability distribution naturally arises in numerous situations in the application of probability and statistical methods. Learning to recognize these situations where the binomial probability distribution can be applied will produce more efficient and effective results. That is, when we're calculating probabilities, the problem doesn't always specifically mention that it's binomial. We need to be able to read and recognize the particular probability problem as a binomial. And if it fits the particular situation of a binomial probability distribution, we can use these binomial probabilities to calculate the results, instead of having to rely upon the basic rules of probability and counting all of the total number of outcomes ourselves.